Dear viewers, welcome back and thank you for supporting by subscribing our channel. In this lecture, let us see the step-by-step procedure of solving a continuous beam using slope deflection method. So let us see the first step, unknown rotations and equations of equilibrium. So in a continuous beam like this, say 2 spans or 3 spans or any number of spans, first step is we need to identify the unknown rotations and then form the equations of equilibrium. To identify the unknown rotations, so the simple rule is in case of fixed support, it is very well known that there will not be any rotation. So see if there are any fixed support in the continuous beam. Say in this example, we have support A as fixed. So theta A, we call the rotation at A equal to 0. There won't be any slope at A. Whereas supports B, support C, they are continuous and support D is freely supported. So these supports will naturally have rotation or slope. So theta B, theta C and theta D are the unknown rotations. So this is how we should identify the unknown rotations in any problem. So this forms the first step. So if there are any number of unknown rotations, we need to form that many number of equations of equilibrium. So to form the equations of equilibrium, the rule is at any support other than the fixed support, at any support say B or C or D, see other than the fixed support, sum of end moments should be equal to 0 for equilibrium. So we can form at B, the end moment this side will be MBA, end moment this side will be MBC. So MBA plus MBC equal to 0. This is at joint B. This is first equation of equilibrium. Then at C, MCB plus MCD equal to 0. This is the second equation of equilibrium. And at D, we have only one end moment MDC, then that should be equal to 0 for equilibrium. So this is the first step in any continuous beam problem. We need to identify the unknown rotations and form that many number of equations of equilibrium. So the thumb rule for unknown rotations is if there is fixed support, there won't be any rotation. All the other supports will have freedom for rotation. That is the rule, thumb rule to identify the unknown rotations. And the rule for forming the equations of equilibrium is here also leave the fixed support. At all other supports, the sum of end moments should be equal to 0. So with this we can easily complete the step 1. And step 2, we need to treat every span of a continuous beam as a fixed beam and then find the end moments which we call as fixed end moments. So the fixed end moments due to applied loads can be found using the following formula depending upon the load case. Say if it is a central point load like this, then fixed end moment at A, we call this M of AB equal to minus WL by 8 and M of BA will be equal to plus WL by 8. In case of fixed beam with non-central point load, say A and B distances, then at the left hand we have M of AB minus WAB squared by L squared and M of BA will be equal to minus plus WA squared B by L squared. Then in case if we have UDL, then fixed end moment is given by M of AB is equal to M of BA equal to minus or plus, that is left side is minus WL squared by 12 and right side moment is plus WL squared by 12. In case of fixed beam with uniformly varying load, then M of AB equal to minus 5 by 96 WL squared, M of BA equal to plus 5 by 96 WL squared. If we have a uniform or linearly varying load like this of this pattern with Q0 intensity at the right end, then the moment at the left end will be minus Q0 L squared by 30. Moment at the right end will be plus Q0 L squared by 20. In case if the load is other way, say if Q0 is here and 0 is here, then this will be minus Q0 L squared by 20 and this will be Q0 L squared by 30. Because where the intensity is more, the moment will be more. So when the moment needs to be more, the numerator or denominator has to be less. So when the denominator is less, you will get more moment. When the denominator is more, you will get lesser moment. So accordingly, we can remember these values. Similarly, a fixed beam subjected to a moment. So if you have a moment M applied at distance A from the left hand, then M of AB equal to MB by L. M into this distance B by L into 2 minus 3 B by L. and m of BA equal to m A by L into 2 minus 3A by L. And in case if you have 2 point loads, then we can separate like this as W1 A1 B1, W2 A2 B2. So when you have non-central point load, we know that the left hand moment will be minus W1 A1 B1 squared by L squared. Right hand moment will be W1 A1 squared B1 by L squared. Here minus W2 A2 B2 squared by L squared. This side W2 A2 squared B2 by L squared. So likewise you can find the fixed moment due to any given loading of the continuous beam. Step 3. Step 3 is the slope deflection equation. An equation which expresses the end moments in terms of fixed end moments and in terms of the end rotations is called the slope deflection equation. So we need to form the slope deflection equation for every span. Say for span AB will be having MAB and MBA. For span BC, MBC and MCB. So likewise MCD and MDC for span CD. So for every span there will be 2 end moments. So here MAB equal to M of AB plus 2 EA by L 2 times theta of near end plus 1 time theta of far end. So MBA equal to M of BA plus 2 EA by L, near end is theta B, so 2 theta B plus theta A. In case MBC, M of BC plus 2 EA by L, near end is B, so 2 theta B plus theta C. MCB will be equal to M of CB plus 2 EA by L, C is the near end, so 2 theta C plus theta B. So this is how we can form the slope deflection equation, or we can find the end moments in terms of the fixed moments and end rotations. In step 4, we need to solve for the unknown rotations. So we have the equations of equilibrium in step 1. So wherein say in step 1 if you see MBA plus MBC equal to 0. So MBA we might have got in the third step. MBC will be having the value in the third step. So we can get equation. Similarly, you can use this equation MCB plus MCD equals 0 and similarly MDC equals 0. So if you substitute these 3 equations, you'll be getting 3 simultaneous equations. So as 3 unknown rotations are involved, you'll get 3 simultaneous equations. So those simultaneous equations can be solved and the unknown rotations can be found. Now, by substituting these unknown rotation values in the slope deflection equation, you will be getting the final end moments. Then the last step will be drawing the shear force diagram with the help of the end moments found and drawing the bending diagram with the help of the end moments found. So this is the procedure to be followed for slope deflection method, and in the next part we'll be seeing a numerical example how to solve a 2-span continuous beam by slope deflection method. Please subscribe our channel and join the mission of nation building with concrete concepts through Learn Easy program. Thank you.